So maybe you don't want it, or you can stop with this. Here's just a nice little overview of how we did that super complicated process to get some wrong kind of ideal equation that kind of tells you how something's kind of right. And that is, we said all pumps look like a circle with a line impeller like this. That's sort of the first step we had to do. Right, is we just do the simplest picture of what a turbo machinery pump is. It's rotating at a constant angular velocity. It has dimensions like this that I know, some diameter, some radii, etc. Okay, and then what else we did? We just essentially, the other thing we did was we neglected the Lys's forces in that entire analysis, because there was we had the sum of the torques essentially that were happening. We didn't involve actually a viscous torque that occurred or any sort of terms like that. Essentially what's happening is we're saying all the fluid's moving so super fast in this case in general that the Reynolds is really big, so I don't need to consider those viscous forces. All I need to consider to model this flow are the Euler equations of motions, where you have that viscosity go to 0. Okay, and then you just looked at one section of this impeller, right? You just looked at the difference between two of these impellers right here, okay? And you had something like that. And since, again, there were no viscous losses, right, it's all plug flow, right? So from here to here, these don't have any curvature to them. They don't slope at all. They're not even obeying the no-slip law. But it's giving you an idea of where these things have to be. And then you have, right, a U1, U2, okay, and then you have a W, that was sort of flow rate, 2. You don't even need to estimate these two things, but you can help it out. So you have this flow rate here. And what we wanted, though, were these V's, the absolute velocities. That's what you're trying to get at, because you don't know what these velocities are, but you know that that's actually what the kinetic energy you have to model is. It's not just the component of these, and it's not just a component of turning the thing on. It has to be some absolute velocity of what the fluid actually gained. That's where you minus this off, by the way. You can kind of see why this difference was minus off, because the only one way to calculate this would be to turn the entire pump off, flow water through it, and this relationship would hold. So maybe if you turn it on, you can kind of see how, well, I don't want to consider the no pump moving condition. So that had the minus term off of it. So again, if you looked at that way to, I'll just put it up there. I'm rambling a lot this one. I'm sorry, but my brain's a bit fried from watching so many presentations. Okay. So then we made more assumptions on the motor, right? And we did this big one, right? This came from that this is nothing. Sort of the no swirl. Right? So this is the equation based on the assumption you get from the fact that you're saying, well, this is going to be negligible. Coming from the fact that, well, I can calculate this to estimate it. The radius for this U1 I know is a lot smaller than this bad boy. And then also for this theta 1, there's a similar reasoning, but it didn't really matter because if this is really, really small, that's enough. It wouldn't even make sense. How on earth would I have more, how would it, this is kind of hard to even imagine if this is the V theta, right? Once you get here, right, this is just going to be smaller tangentially than this one, right? You could look at the vector magnitude as well to derive the same result. But there was justification in this no swirl to at least ignore it, and then it was well, how on earth do I describe this theta 2 velocity term? This one's not bad. It's an angular velocity and a radius. I can measure a radius. I can input power to convert to an angular velocity. I'm good there. But what about that thing? That went down to geometry, and you drew a triangle, you drew this velocity triangle really to just get that expression to relate this in terms of a difference of quantities. That gives you, right, that gave you the ideal pump curve. The ideal pump curve in terms of parameters that you can design that you can estimate in a first stage of design, which is a linear approximation to your flow rate equation. Linear approximation to your head loss equation. Remember I said you could always estimate what it is by any given polynomial. This expression right here is the best first coefficient you could have. So this is a first term approximation. You're in a Taylor series, they go up in powers. This is a linear approximation. Okay, so that is the ideal pump curve. And then the other thing that we got to before this one was this way to rationalize your shaft power. But I wanted to put that one up first because I think that's the most important part of this whole video and the most important part of derivations based on complicated physical systems. Okay, so then here, also have a way to estimate this, and that was this. No, it's not. It's not. Sorry. Don't ever do that. Don't ever do that. Very common mistake. Right? It's not parentheses squared. It's the difference of the squares. Don't ever do what I just did. Ever. Okay, and this is the other kind of big equation we got to, and it was a way to rationalize, right, sort of the power required for the shaft based on these velocities you're considering. So many sort of conceptual questions can actually come from this, because if you're trying to judge what's more powerful, you can kind of guesstimate what these differences are going to be, and then you can get an idea of what that is. So you're sort of right. So you're showing that this could be right, and it's this difference that really can just compare two different terms. Right? You can compare essentially two different designs based on this, regardless if you knew that. Right? You could just really show by orders that, like, well, I could rank them based on the differences on this one. And those are really the two equations we arrive next. Okay. Next, we're going to use them more. We're going to draw more graphs that are going to be involved in the pump selection process. So as of now, we just have one. And it's the most important one, to be fair. QH. What we have is we drew this curve right here. In reality, that's the one we care about. So this is actual ideal formula. Right, so we have one there. In your project for project 2, I actually was going to give you a bunch of diameters to maybe like get a first basis approximation based on like those, but decided to not do it because I just have more. There's just more layers involved for how these curves combine. So I don't even know if you have any homework problems assigned for that ideal head loss formula, but I decided to leave it out. Because really, you always are just going to use the actual. So I focused on like, how about we look at actually getting actual pump curves. So this is just one that we have. And we're going to just keep adding lines to this graph, and then all those lines logically combining can give you the best pump for your project. And that's what your project is going to be about. It's going to be about making a bunch of lines and changing those lines based on Excel sheet parameters that you tweak and turn. You should kind of in the moment see how the curves change, and then you could just pick the best pump graphically in your project 2. Actually, if you had it set up like that, you could definitely solve all of project 2 by getting all the curves set up, changing a cell value, and just tweaking all these intersection points to make them good for you. That's one way to do it. There is a mathematical solution to the second problem, though, that I got. You don't have to get that, though.